computer science, and so you will tell us about this neighbor searching and applications.
Yeah.
Go ahead.
Okay, so thanks for inviting me for talking here. So basically I'm a computer scientist, and I'm one of these people that actually works on like core algorithms and core data structures. So I like in one of the previous talks we already heard things about like matrix multiplication, that this was somehow important, and dynamic programming. And basically like what I typically do is like figure out how you actually get these core algorithms to run. And so, in particular, like the problem that I actually wanted to talk about today is dynamic nearest neighbor searching, right? And why this is useful. So, what is nearest neighbor searching then, maybe? So, the idea is, so suppose that you have some set of points P in the plane, and you want to store this set of points in some way in your computer system, such that if I give you a query point Q, right, so this somehow a point that is not in the set, you can very quickly find the closest point in P to it. Right, so as an example, so here's my blue set, so this is the thing that I give you, right, and you somehow should store it in some way such that when I give you a query point Q, you can very quickly find this point P that is somehow the closest point to Q. Right, and the idea will be there will be actually very many of these query points. Right, so and somehow the key game is storing my sets in such a way that I can ask these queries quickly. Yeah. So I guess you might now have two questions. One is, so why would I possibly want to do this? Right?
I think the color suggests an example.
The color, there will be examples. So that is
The nearest orbit.
Yeah. Well, there we will do. Oh, we're very close. The other problem is you might wonder, okay, so why is this a problem? I already know a way of solving it. Right, and that's also something that we will see. But first, why? Right. So why would you want to do this? And so typically this problem is actually known as the post office problem. And I see some young people in the room, so let me maybe explain what a post office is, right? So this is this thing where, like in the past, when you had your physical letter that you wanted to send to somebody else, right? Then you went to this place called the post office, and there they sent it to the person that you wanted to send to. And then the point is, of course, that you don't want to walk too far with your letter, right? You want to go to a near post office. Now, maybe a more modern example is, so maybe these blue points, they are not post offices, but maybe they're some sort of antennas or towers or whatever, and my query point is, let's say, a cell phone, and I want to find the closest cell tower to connect to, right, so that I have the best signal or something like this. Or maybe my points, they are power stations, right, and my query point Q is actually, let's say, a robot or something like this, that has to charge, and I want to find the closest power station to go to charge. Or maybe even my blue points, they are, let's say, hospitals, and my red point Q is this place where I am, wherever I lie dying on the ground, and I want to get to the closest hospital, right? And I want to know which one to go to.
What's the point if you lie dying?
Yeah, okay, maybe just before I die. So I guess in all of these scenarios, there are sort of two properties of the solution that we want, right? One is that the solution, it has to be correct, meaning I want that whatever answer you tell me, really this point is actually the closest point, right? I don't want to be like near to dying on the ground, and then my phone tells me to go to some very far away hospital when there's actually one around the corner. Yeah.
So I keep thinking about Google searches. So the hospitals might be web pages, and my queue might be my specific Google search. But of course those can be very different, and there's maybe, so now with the correct, there might not be a correct but is this something I should keep in mind, or should I just forget about this comparison?
In some way, I mean, you can think about it in this way, but sort of the thing is always that we're these points, they live in a particular space, right? And this space defines some sort of distance measure, and I'll mostly talk about sort of geometric spaces where it's easy to know whatever this distance means, and actually also in general, for most of the talk, I'll talk about two-dimensional spaces. And embedding this kind of web pages, I mean, there is also some sort of nearness, but it's more difficult to embed that in this world.
Yeah, but also important.
Yeah. Oh yeah, so right, so one is, well, I want to be correct, right? That's the most important point. Whatever the answer, it should be really the closest one. The other point is, I want this solution to be efficient. And with efficient, like the most thing that it will sort of mean throughout the talk is that I can answer these queries quickly, right? How much time it actually takes me to find the closest site. That's sort of the main thing I'll care about. Okay, so that's sort of the why, right? So okay, so here's my general problem, like group points and store them in some way such that given a query point, you can quickly find the closest point. And then you might wonder, well, sure, but what's the problem really, right? I mean, here's these blue points, and they're just points, and they have some coordinates, and I don't know, I just store them in some list or array or whatever. I mean, if you've ever programmed, then pick your favorite data structure, and then, well, you just go like through all of the points one by one, right? And well, you compute the distance from, let's say, this red point to the blue point, and well, while doing this, you maintain whoever is closest. Easy, right? Okay, so if you then do this and you sort of see what happens if I plot, let's say, the running time of my query algorithm, right? So how much time it actually takes to find the closest one, to the input size, so how many blue points I have, then you'll see this sort of linear relation, right? So if I have n input points, then it will take me something like n or 2n, or I don't know exactly how many n steps or comparisons or whatever you want to measure, and that's okay. And then if I double the input size, so if I now have suddenly if I have twice as many inputs, well, then my running time will be something like twice as high. Right? That seems fair. And then you might say, okay, well, good, problem solved. But the thing is that you can actually do much, much, much better. So what we'll actually sort of argue is that you can get like this sort of scaling behavior of the running time that is something like order log n, meaning that if I have n input points, I can actually do something like log n comparisons to figure out whoever is the closest one, provided that I store my data in the right way. Yeah? And like even in this type of drawing, even there's already like this huge difference. I should actually point out that sort of I lied to you, because this green line is actually higher than it should be, right? It's even smaller than whatever is drawn here, but then, well, you didn't really see.
It's because it's the axis.
Yeah, it's pretty much on the axis. Okay, so so how would you sort of do this? How would you get these super fast queries? And well, there's sort of I'll just sketch the main ideas. Main idea one is you build what's known as a Voronoi diagram. Right, so a Voronoi diagram, it's like a subdivision of the space into these cells. Every point gets one cell, and in such a way that if I look at the cell of a particular point P, then all of those points in this cell, they will be closer to P than they are to any other blue point. Yeah? And that basically means, so if I were to somehow store this Voronoi diagram, right, this subdivision, and well, for every cell the point that it corresponds to, then what I can simply do is, well, if I get a query, then, well, I have to find the cell that now contains the query point. Right, then I go there. Now, well, the second part of sort of why this is actually fast is because this problem, like locating in which cell a particular point lies, that is something that I can do very fast. So again, sort of what is sort of a very high level, what is the main idea? Well, the idea will be, let's say that I draw a vertical line through every vertex of the Voronoi diagram, so through every, let's say, this point where three of these edges meet. I draw some vertical line, right, and I draw lots of them, and I store them, right? This is part of the stuff that I store. Then, once I get a query point Q, this Q guy over here, then what I claim that we can do is we can very quickly find the vertical strip that contains P. Right, so basically which of these two lines, the one that is directly left to keep, the one that is directly right to keep. And so this is something that we can do in this log n steps. Main reason for this is because now, so that if you already think about this a bit, now the y coordinate where my point is exactly doesn't really matter anymore. Okay, so well, once I have this, then you sort of have a similar thing, right? So there's all of these edges or segments of the Voronoi diagram that somehow cut through this vertical strip, and all I have to do is sort of figure out in which part of the strip I am, which of the part of the strip my query point is. Right, and again, I claim that somehow finding this point you can do very efficiently, like in log n. Okay, so that's sort of very, very hand-wavy and very briefly, like how could you get fast query times? Is that a question?
No,
Okay. Okay, so basically, right, so far what I told you is nearest neighbor searching. Right? My title of the talk was dynamic nearest neighbor searching. Right, so what's the dynamic mean, or when does the dynamic come in? That's essentially when this set of points that I'm trying to store is dynamic. Meaning I can insert new points, new blue points, right? So maybe here I add a blue point, or I can delete blue points, right? Wow, go on. And again, I want to somehow make sure that I store these blue points in such a way that once I get a red query point, I can quickly find the closest point. So again, sort of the same two questions, right? So why would I possibly want to do this, and or why is this useful? And well, I mean, what's the problem? I mean, we just saw this Voronoi diagram business, right? So why not use it? So why? Well, here's the example with the blue points. So suppose that my points are not actually points, but let's say shops that are selling some sort of item. And maybe I want to not just go to the closest store, but I actually want to go to the closest store that is currently open. Right? Store is open and closed, and it doesn't really make sense for me to go to one that is closed. Or maybe I care about a particular product, and actually want to go to the closest store that has this product in stock. Right? I don't want to go there if they don't have it. Right? And again, if a store has a product in stock, that is something that changes over time, and that means that I sort of add shops that I care about, or delete shops that I care about. Or again, if we go to this example with the power stations, if I'm a robot and I want to charge, then maybe I don't want to go to the nearest power station because there's already some other robot charging there, right? Meaning that this station is not available, but I actually want to go to one that's free. And which one is free is again something that changes over time. And well, again, kind of the message here, right? The important part is that the solution that we get for this thing is correct and it's efficient. And I don't want to run out of battery while trying to go to a place that I shouldn't be going to. Yeah?
So in your examples, you've got this sort of pre-existing fixed set of points that can come and go.
Mm-hmm.
Is that the general case, or is this supposed to be like sort of a whole space that might suddenly have a new shop open up or something?
So in principle, the whole, and anywhere in the plane, a new shop can pop up or appear. But okay, in my drawings, it's usually I pick them from a fixed set. But in general, I care about all of them.
Okay.
Other question?
Yeah, I thought dynamic meant moving around. Are you going to get to that, or?
Yeah, I will also get to that.
But it's sort of a discrete model of
At this
moving
point,
around.
it's discrete changes, right? There are, there is, at any moment in time, there's a fixed set of sites, and there's discrete events at which this set that I care about changes. Okay, so, well, great, right? So, well, what's then the problem of using this Voronoi diagram method that I just talked to you about? And there, basically, the thing is that it might be very, very expensive to update the Voronoi diagram. Right, so here's my drawing of a Voronoi diagram. Now, if I insert some new point, then sort of what it means that I have to do is I have to insert all of these thick line segments or edges in my diagram, and I have to remove the dark blue parts, right? The parts that are no longer part of the Voronoi diagram. And then, basically that can be very expensive because what I have to add or remove, there might be very many components. Like there might be linearly many things there. For example, if my points happen to be like almost on a circle and I add some point in the middle, then pretty much everything inside this disk has to change. There's lots of changes, and well, if I somehow have to do them all, then this takes time. So, so basically meaning this Voronoi diagram explicitly, that's not such a good idea. However, let me tell you like a very simple idea that will sort of get us quite a long way in solving this dynamic problem. And well, the idea is that it's very simple. So what I do is I partition my set of group points into subsets, into small groups. Right, so every group I give some separate color, and now I have a bunch of roughly equal sized groups. I make sure that all groups are more or less the same size. Right, and now for every group individually, I just build a Voronoi diagram. Okay, right, so this one, and then if I get a query point, so if I want to answer these queries, then well, then I locate the cell in each of these Voronoi diagrams. For every group, I just locate them, right? And this gives me one candidate point for every group. And those candidates, then I just naively compare them all and report the closest one. And so in terms of query time, I mean, it's kind of decent, right? It depends on how many groups I have, but querying within a single group is very fast because this is this Voronoi diagram business. And updating, well, updating is also not too bad because now I only have to add my points to one of these many groups, right? And that means that I can only have to update the Voronoi diagram of one group, which is also not too bad. So then, if you look at this, well, this sort of running time input size diagram again, then you'll sort of see that if I look at the query time, you can more or less get anywhere within this range, right? If I somehow, in the extreme case, if I only partition into one group, right, then I get very fast query times because then I have the entire Voronoi diagram stored. But then somehow, like, well, updating the thing would be very slow, so that would be very high again. On the other hand, if I make very many groups that are very small each, well, then, well, my query time will be horrible because I have to try each group. But on the other hand, like, updates will be very fast because every diagram is very small now.
Technically, it's order n, right?
In which is it?
Well, what I mean is that you always, given group size, you have more groups scaling with n, and so your algorithm will eventually scale linearly in n. Right?
No. So here comes the trick. So
Okay.
if you pick your group sizes right, meaning that if you pick them roughly square root n, then you can get
Okay,
both square root n query time and insertion time.
if you don't keep the sizes fixed, yes.
Yeah. So that's the part that's definitely missing, right? So you have to be careful how you pick the group sizes. Yeah.
Sorry. Now you add one point.
Mm-hmm.
But actually in your picture you have multiple gray ones and not, so
Mm-hmm.
you have to multiply it by that or something, right?
Well, so basically this is for the version where I add or remove 1 point or 1 point at a time. If there would be very many points at the same time that either go off or on, then you can do something slightly more clever than what I've just shown you here. But let me maybe not go into that now. Okay, so very basic strategy, just split things into groups and treat those groups separately. Sort of gives you like a huge reduction in the query and update time compared to doing nothing. You can even do better. So more or less like the state of the art is something like you can get log to the 4th n operations per query or update time. I won't tell you how this works because it's complicated. Let's look at sort of variations or extensions to this thing. So in my robot problem, right, where I had I set up my robot and it wanted to go to the nearest charging station. So far we sort of said, well, there's these points and the robot, and well, there's nothing else, right? So I can just like move directly in a straight line to the closest site, but that's probably not how it works in reality. Right? There's probably some sort of environment, like these robots, they're moving inside them, some sort of factory floor or whatever. And, well, I mean, like, the robot cannot walk through walls, and it has to avoid people and other objects. So you actually have to sort of go all the way around. Right? So what is the closest, like the distance to the closest site, it might not be this simple Euclidean distance that we talked about so far. Right? Or even, well, I mean, in the Euclidean case, right, if there's no obstacles, then this was the closest one. But actually, if I take these obstacles into account, then now suddenly this guy might actually be the closest one. Right? So the environment actually matters, and somehow, if you want to incorporate these environmental constraints, then the problem again becomes more difficult. Other type of extension is the thing that was asked about before. Maybe my robot, it doesn't want to go to a power station, but it wants to meet up with some other robot that is also moving around. Right? And now we have these blue points that are continuously moving around, no more discrete events. And then again, somehow, the problem becomes much more complicated because, well, I mean, I cannot really explicitly maintain this diagram anymore. Right? These somehow where these boundaries are, that changes continuously, which makes the problem more complicated. So, well, again, a variation, and then, of course, you can even look at the combination of the two, right? What happens if my points are moving continuously, but they actually move inside some complicated environment? Right, and basically for all of these versions, I mean, we know something to do, or how to deal with those. I mean, we don't have the complete picture yet, and we don't get the full, this super log n bounds that we can get for the static problem, but there is stuff that we know how to tackle with some of these problems. Okay, so sort of wrapping up is, like, I think one of the reasons why I sort of started to look into these problems is actually because I talked to an ecologist at something like a day like today. And so basically he had some problem that, I mean, they were observing where animals were, and they had some sort of locations where they had sightings of some sort of animals, and they knew where animals were currently, and then they wanted to figure out for every previous location where they could have gone to today. And then there were these additional constraints, again, that somehow that from every location you couldn't directly, or which current locations were available, whatever. I mean, this is some sort of complicated process which I don't know the details of because I'm not an ecologist. But basically he had this problem for which this dynamic nearest neighbor searching data structure was like a key component in the solution. So basically message is, well, thanks again for organizing today and for sort of bringing us all together in a room. And if you somehow have problems that are of this nature, then I would be very happy to talk to you about any of these things, or general algorithmic problems. Right, and basically that's it.